All right, then. This is our last discussion in our series for per unit quantities, for now at least. And we're going to be discussing about changing the impedance base. This is a very specific case scenario that needs to be accounted for, and I will get into the discussions of how or why we need that and solve an example, and we'll hopefully help you better understand why this is needed. But before I begin, I'd just like to encourage everyone to subscribe to our YouTube channel if you haven't already done so. We have free videos every week on this topic of power engineering. So if you're interested, definitely subscribe. Also visit our website movingelectrons.com. There are tons of other free resources there. Sign up for our newsletter as well. That'll keep you up to date with all the changes that are happening. Also, I'd like to mention, if you've seen my earlier videos, I leave a sample problem for you to solve at the end of every video. I'll do that today as well. Feel free to solve that sample problem and leave your answers in the comment section below. Those are generally very easy to solve. They relate to the video and the discussion that we do that day. I generally solve a similar problem in the videos as well. So definitely do that. Also, if apart from those sample problems, if you have any other questions or comments with reference to the topic that we're discussing, please feel free to ask those via the comment section or send me an email using the email listed on the website, and I will get back to you as soon as possible and to the best of my knowledge and try to help you guys out if I can. All right, then. Let's do a quick recap. So far what we've seen in our earlier videos, we've defined per unit quantities as being actual quantities over base quantities. We've concerned ourselves with four electrical parameters, namely voltage, current, power, and impedance. We've also defined bases for circuits that have transformers and seen how per unit quantities are really helpful there. We've established the laws of defining the bases for the voltage and power based on the turns ratio. I will use this formula, and we've seen this formula earlier, so I've written that down here, so it's a quick reference for us. Where an impedance base, we've defined it as being the square of the voltage base over the power base, and when you put the units in there, we see that that basically is kV square over MVA, or kV square times 1000 over kVA. I discussed this a little bit more in detail in the videos where I started talking about transformer bases, so you can go have a look there if you want a little bit more detail. But I've just written that down here for a quick reference because we're going to be using that today. All right, so what am I talking about changing the impedance base? What does that mean? Why do we need to do that, and how do we do that? So let's assume, again, let's go back to our transformer. Let's assume we have this transformer here, right? This is a transformer circuit. Let's say it's 5 kV on the primary and it's zero point 0.6 kV on the secondary side. Let's say you're given an impedance of 5%. The transformer manufacturer comes and says, okay, you know what, the per unit impedance is 5%. What does that mean? I've discussed this before. 5% is nothing but 0.05 per unit, right? Per unit is nothing but basically a percentage on a certain base. So let's say he's given you this, but the question you need to ask him is, what base are you defining this on? And generally, the transformer manufacturer will tell you a certain base. So they'll say, okay, this 5% or 0.05 per unit is at a base value of, let's say, 2000 kVA, right? So you're given 5% at 2000 kVA. Let's assume the base is not 2000 kVA. Why would that be? Let's say this transformer has a fan cool rating. Now, what's a fan cool rating? Okay, we'll get into that. So let's say this is what your transformer power rating is. So when you see something like this, that means this is the base rating of the transformer, and this is a fan cool rating of the transformer, right? So what does it mean by fan cooled? So when a transformer rating is given 2000 kVA, let's say, what does that mean? That basically means the transformer can transfer 2000 kVA of power. Any more power, if you try to transfer that through this transformer, it'll start overheating, and that's not good for the components, the physical transformer itself. So there are certain transformers that have this option of installing a fan on them, or they can come from the manufacturer if you order it with the fan, where they say, okay, when it exceeds 2000 kVA, I turn my fan on, and then it allows me to transfer up to this much power, this much extra power. So let's assume this transformer has a fan cooled rating of 233, 2333 kVA, right? The reason I chose that funny looking number is because that's a standard rating if you look up a transformer manufacturer. Okay, so now you're given an impedance of 5%, but the manufacturer says it's at a 2000 kVA base. Let's say I want to use this complete capacity of the transformer. So I want to change my base to 2333 kVA. What would my impedance be at this base? I need to find that out, because as I'm analyzing my circuit, let's say it's further down connected to either another transformer, right? So now you have a more complicated circuit, there's a load there, and then this is the circuit you have to calculate. Now you're given an impedance on this base, but you're using a base which is higher. So I cannot use 5%. I have to convert this 5% to this particular base. How do I do that? Okay, let's derive that formula of how we are going to do that. So let's derive the formula for that. What do we know so far? We know that Z per unit is equal to Z actual over Z base. We know that much. What else do we know? We also know that Z base, so let me write that here. Z base, as I've written here, is nothing but kV base square times 1000 over kVA, the power base, right? So we need to know these two things. Let us then write our equation 1. Let's define Z per unit. Let's call it the original value, right? So OR for the original value, which is given to us here. But let's just write down what the formula for that would be. So that is Z actual over Z base, and we're just going to substitute Z base here. So that becomes Z actual. Z base is in the denominator, so here this will become kVA base here, just turning this upside down, and kV base square times 1000. What I'm going to add here is the OR and the OR, right? So then that is basically telling me this is the original base, power base, and the original voltage base. And that becomes my equation 1. My equation 2 is going to be where I'm going to write what my new, so I'm going to write that with N, is going to be the new per unit impedance on the new base is going to be Z actual, and we're going to write kVA, the power base, which is new, the new power base over the new voltage base square times 1000. That's going to be my equation 2. Remember, Z actual is going to remain the same. Z actual, remember, is the physical impedance of the transformer. It's a physical property of the transformer. It is not going to change. The per unit impedance is a mathematical quantity that we have created based on this formula, which is defined by the bases, by the impedance base, which is the power base and the voltage base, right? So that's a quantity that can change, but the actual impedance is not going to change. And we are concerned only with the per unit quantity, because we need to find the per unit quantity because that's so much more easier to solve, allows us to solve electrical circuits that much more easily. Okay, so now that we have that clear, okay, sorry about that. Okay, let's do this. Let me change the color and let's do equation 2 over equation 1. And just by doing some simple arithmetic there, just simple algebra there, we are going to get this formula right here. Original, we're going to get, so this um, is here, right? So we're going to basically get kV base original over, remember you're doing 2 by 1, right? Equation 2 over 1. So this remains in the denominator. Z actual will cancel each other out, the thousands will cancel each other out, and this would be kVA base new over kVA base original. Let me write new a little bit clearer. So there you go. That is your formula that you need to know, that we've derived right now, that is going to allow me to change my impedance from an original value to a new value. How is that? Because we already know this value. The original value per unit is given to us. We know the original basis. We are going to define a new base. Based on this new basis now, this formula allows us to calculate the new impedance. Let us quickly solve the example and see, that will make it a lot clearer for all of you. So let's go back to our transformer. What have we been given? We've been given an impedance of 5% at 2000 kVA. We've been given the base as 5 kV on the primary, and so let's use this information. All right, so let me solve this example here. So we are given Z per unit original as being 0.05 per unit. kV base original is going to be equal to the kV base new. In this case, in a transformer, you'll see the sample problem I'll give you different voltage bases, so you'll see an example of that as well. But in this case, it's going to be the same, which is 5 kV. So that's the base. My power base now, so my kVA base original is 2000 kVA, and my kVA base new is the new base that I wanted on, which is the fan cooled rating for the transformer, which is 2333 kVA. So we've given all this, so just plugging all the information in the formula, we're going to get our new impedance is equal to this 5 kV over 5 kV square, and then the new base, which is this over 2000. Basically this gives me an answer of 0.06, at least approximately. I think it's 0.058 or something is what it'll give you. So this allows you to define a new impedance 6% at a base, at your new base of 2333 kVA. So there you have it. That's how you would use this formula. It's very simple. All I wanted to show you that it's possible. This is how we derive the formula. This is what the formula is. That's what I want you to remember. And this is how we use to calculate the new impedance, and you see there's a difference in the impedance. So if we go back and try to solve this circuit, let's say you're given this circuit and you're told to use this base 2333, that's the power transfer that's possible. You will use a 6% impedance rather than a 5% impedance. So you have to be careful. Always ask this question: if someone's given you an impedance, what is the base for that impedance value? All right, so now that we're clear on that, let's me give you a sample problem as promised, and then you can solve that. Leave the answers in the comment section below and we can continue this discussion forward. So let me say, okay, so far you've seen a transformer. Let me say there's a generator. Every generator has what's called a subtransient reactance, and we'll probably deal with this if you haven't seen this before. I'll talk about probably generators at a later date, and you can go refer to those videos, or you might have already heard of this in your classes or in your studies before. So there's a subtransient reactance. Let's say you're given a subtransient reactance of zero point 0.1 per unit, and this is given at a nameplate uh, rating. So there's a nameplate for the generator. The nameplate is, let's say it is 11 kV and 1000 MVA, right? So this subtransient reactance is given to you at this rating, but what you need to do is find me the subtransient reactance per unit value at a base, because let's say the system that we are solving is being solved at a base rating of 13.8 kV and 2000 MVA, let's say, is the power base. So given this information, you have to find out the new subtransient per unit value, and it should be very easy. Just plug and play into that formula, and let me know what your answers are. All right, once again, thanks for joining me, and have fun. Take care.